basic picture is this. So I have a particle or drop. Right now it's of this, so it's difficult to imagine a drop like this, but this is the idea. There is a disperse phase constituent at a given temperature T naught. It's sitting in an ambient at a different temperature. So I could replace these by concentrations. So it becomes a mass transfer problem, but I'm going to stick to calling them temperatures. Okay? And so there is heat is diffusing from the surface of this drop. It has a length scale A, and there is a flow that the drop or particle is subjected to. And the question we ask is, what is the rate at which heat is transported from the particle to the ambient, and how does it depend on some suitable non-dimensional measure of the flow strength. Okay? So this is the basic problem, and we'll start with a simple scenario and then try to add complexity to that problem. Okay? So like I said, this is important in a range of applications and suspension polymerization, where you start with monomer droplets and it polymerizes, so the viscosity of the drop increases as a function of time. It's an exothermic reaction, so you want to transfer heat efficiently due to agitation. Then there's spray drying, spray coating, liquid-liquid extraction. And this is also important in fuel droplet evaporation in combustion engines. Okay, that's a mass transfer problem. So it's relevant to a range of applications. Right. So the objective is this. So we're going to try and see what form this relation takes in different scenarios. Okay, starting from the simplest. So here Nu is the Nusselt number. So it's the rate of heat transport in some non-dimensional form. So in particular, it's made non-dimensional by the rate of heat transport when only conduction acts, when only diffusion acts. So it's essentially the rate of transport in conduction units. So when there is no flow, the rate of transport is 1 conduction unit. Nusselt number is 1. Okay? So in general, when we have a flow, we expect Nusselt to increase from 1. Okay? And Nusselt would in general be a function of the flow. So that is via the Reynolds number. Okay? So that we know as the relative dominance of inertia and viscosity. So that's the Reynolds number. And then it's a function of also the Peclet number. So the Peclet is the analog of Reynolds number for heat transfer. So it tells you the relative dominance of convection of heat to conduction. Okay? So the Reynolds number is the relevant velocity scale times the length scale. So here the length scale would be the size of the particle by the momentum diffusivity or kinematic viscosity, and the Peclet number would be the same thing, except I replace the momentum diffusivity by the heat diffusivity. Okay? So and you can either talk of Reynolds number and Peclet number as the governing parameters that decide the Nusselt number, or alternately you could talk of a Prandtl number, which is just the ratio of the two. So this really tells you how efficiently momentum diffuses relative to how efficiently heat diffuses. Okay? So in particular, generally for mass transport, the Prandtl number, which is called the Schmidt number there, is much greater than 1, because mass moves very slowly in comparison to momentum. Okay? So it's in several cases, particularly related to mass transport, it's possible to have the Reynolds number being fairly modest, but the Peclet number will be very large. Okay? Because momentum diffuses rapidly in comparison to the rate of convection. So Reynolds is not very large, but mass diffuses very slowly, so Peclet can be fairly large. Okay? So the idea is to find out Nusselt as a function of these parameters. There will be additional things. For instance, for the drop, you have to worry about the viscosity ratio. What's the drop viscosity to the ambient viscosity? There will be some parameters that govern the nature of the flow. I have to have the information about how the flow looks. Okay. So this is an example of typical correlations. So this is a flat plate immersed in a uniform ambient aligned with the plate. Okay. And this is the heat transfer at a station x, so at a distance x from the leading edge. And this is the case in a laminar flow. We'll see that this actually can be arrived at by simple arguments. Okay. This is an empirical correlation similar to this, but in the turbulent regime. Okay. So you can see in general Nusselt might start off at 1, but it typically grows like a power of Reynolds and Prandtl or a power of Reynolds and Peclet when the Peclet becomes very large. Okay, so the heat transfer becomes increasingly efficient as the flow becomes stronger. Right. So again the same picture, but here what I want to emphasize relative to the earlier picture is the fact that now we are going to consider the drops being fairly small, which is typically the case. So the idea of the small thing is, smallness is that, so how small is small? The drop length scale is much smaller than any length scale that might characterize variations of the velocity in the imposed flow. Okay? Now this has the advantage that though the flow on the large scale would look fairly complicated, like I have sketched, on the scale of the drop, it starts looking much simpler. Okay? Because what you essentially do is, because A by L is small, you can expand the velocity field in a Taylor series about the drop. And the first few terms of the Taylor series capture the local form of the flow, which is simpler than the global form. Okay? So if you do this, okay, so like I said, the complicated large scale flow looks simpler on the scale of the particle or drop. And the idea is that you expand the complicated flow, which is V, which is a function of x. And the idea is, at first you expand it, let's choose a particular point in the drop. The center of the drop is a sphere, or a particle is a sphere. At leading order, it should be just that velocity evaluated at the center, plus a linear variation, quadratic variation, and so on. Okay? So I'm going to be talking about these two leading order terms. Okay? The effect of the constant slip relative to the particle or drop, and the effect of a linear flow. A linear flow meaning the velocity is just linearly dependent on the position coordinate. Now this constant term would arise typically when there is a net density difference between the particle or the drop. So it sediments relative to the ambient, and so I have to worry about the slip term. Okay? Now in cases where the drop's density difference is not very large, and when it's exactly 0, these are called neutrally buoyant particles or drops, then this term goes to 0, and I have to only worry about what the shear does. Okay? So those will be the two cases we consider. Okay? And the further consequence of assuming a very small particle or drop is that, remember, the Reynolds number was defined as being proportional to this length. Okay? So when the drop becomes small, the Reynolds number becomes small. Okay? So we are going to start with the simplest case. Okay? And for the most part, just stick to this, where we say Reynolds is much smaller than 1. Let's just say it's 0. Okay? So we are in the Stokes flow regime. Okay? And if we are in the Stokes flow regime, then this is the equation we are going to solve. Remember, we are going to look at the effect of convection on heat transfer. So the governing equation for the temperature field is a convection diffusion equation. And if you remember, this plays the Reynolds role of the Reynolds number in heat transfer. So Peclet measures how large this convection term is, the temperature being convected by the velocity field, relative to the conduction term. Okay? So that's the PDE that we want to solve, and these are the boundary conditions. So we know the temperature on the particle or drop surface, and we know that it relaxes to temperature of the ambient far away. Okay? And I'm only going to talk about the exterior transport problem, which is the only thing for a particle, but a drop can have an interior resistance, but I'm not going to be talking about that. So this is the equation. These are the boundary conditions, and importantly, U here is fixed. Okay? It's not dependent on the temperature field. So the momentum transport is decoupled from the heat transport, and we just said that we are going to be in the Stokes regime as far as the flow is concerned. Okay? So Reynolds number is 0, and that velocity is assumed to be known because it's governed by the Stokes equations, and that we can solve. So we can solve it a priori and then use that velocity field in this problem, okay, to solve for the temperature field. So now the Reynolds is fixed, okay, and we remember we had the luxury of we had two parameters apart from other physical and flow parameters, Peclet and Reynolds deciding Nusselt number, but we have now set Reynolds to be 0, and therefore the Nusselt is only going to be a function of the Peclet number. Okay? So with the Stokesian assumption, it is this functional form that we are going to set out to find. And we have two problems, like I said, where there is a net slip velocity, so the fluid is streaming past the particle or drop. And here the Peclet is defined as AU by D, where D could be the mass diffusivity or the heat diffusivity. And then we have a linear flow. So in this case, what the linear flow gives you is a time scale. Okay, so the time scale is the inverse of the shear rate, and I've denoted the shear rate or the characteristic magnitude of the velocity gradient as gamma dot here. So if you say that the shear rate is gamma dot, then the velocity scale for shear flow is gamma dot times a length scale, which is A, and therefore U here is gamma dot A, and the Peclet becomes gamma dot A squared by D. Okay. So we know what the respective Peclet numbers are, and we are going to try and find what Nusselt is as a function of Peclet, and we are going to do it not numerically. So we are going to do it in two asymptotic regimes. Okay. First when Peclet is small, the other when Peclet is large, and then piece the two things together to try and see how it varies over the entire range. Okay. So that's the objective, Nusselt as a function of Peclet. Okay. And like I said, we are going to first try and see what's the functional form for small but finite Peclet in translation and when there is a linear flow, and we are going to repeat that exercise when Peclet is large. So this is the typical curve. So I'm just going to tell you, anticipating the results we'll see. Okay, remember, when there is no flow, so no flow corresponds to Peclet of 0. Okay, Nusselt is just 1. It depends really on how you non-dimensionalize it, but we are going to say it's scaled such that it's 1. It's 1 conduction unit here, and then it starts to increase, and typically it grows with the power of Peclet when convection becomes dominant. Okay, that's what we saw in those empirical expressions. Okay. Right. So we are going to start from the really simple case when there is no flow. Okay, just to set the baseline, Peclet equals 0, and the convection diffusion equation that we saw earlier, there Peclet is 0, so we have only the conduction term, right? So we have just the Laplacian of the temperature field equaling 0 with boundary conditions. So that's like a Dirichlet problem for the temperature field. And since we have simplified this thing to just a spherical particle, just have the radial part of that Laplacian equal 0 with t equals t naught and t equals t infinity. Okay. And the solution is very simple. You can solve that and show that the temperature is 1 by r. Okay. The deviation from the ambient scales like 1 by r. In other words, you can see that when r is 1, so I have scaled r with a here. So r equals 1 implies I am at the surface of the sphere. Then this is 1, so t must be t naught, and r goes to infinity, this must be 0, so t goes to t infinity. Okay. Now that it's 1 by r merely arises from conservation of flux. So this, what that implies is that the flux through any closed surface must be the same, because there is no accumulation at steady state. The area of the surfaces grows like r squared, that's just the area of a spherical surface. So the flux must reduce like 1 by r squared, so that the flux times the area is a constant. But the flux is given by the gradient in temperature, so the gradient in temperature must decrease like 1 by r squared, and therefore the temperature must decrease like 1 by r. Okay. So I know the temperature field, and now I calculate what's the heat transport from the surface of the sphere. Okay. So that's just Fourier's law, thermal conductivity times the normal component of the temperature gradient integrated over the area of the sphere. Okay. So it's all non-dimensional, so this is really the solid angle element, and if I do that, I get this to be the total heat transport from the sphere. Okay, you could have guessed this part just from scaling analysis. Okay, this is the driving force after all. T naught is different from T infinity, that's why there is a transport. And then you have K times A. So you say that it's K times the temperature gradient, which is T naught minus T infinity by A, times an area A squared. So what the solution really tells you, and even this is not difficult, is 4 pi, that's the area of the unit sphere. Okay. So I'm sorry, that should be plus Okay, so what the form of the solution also tells you is that there is a convenient way to define a non-dimensional temperature, right? Instead of talking about T itself, I can talk about this non-dimensional combination, which must be 1 at the surface and 0 far away. So that's always good. I have 1s and 0s. Okay. So we know what the advantage is, now we know what the heat transport due to conduction is, and therefore we know what we don't know the actual Q when Peclet increases from 0, but what we want to define the Nusselt number is that unknown Q by this conduction estimate. So that when Peclet is 0, the Nusselt is 1. Okay? That's all. So this serves as the finding the proper conduction unit. Right. So we come back to the convection diffusion equation, and since we know the conduction solution, we now have the definition of the Nusselt number here. Here now Q is a function of Peclet that we are going to try and find. So this is the non-dimensional statement. We have the non-dimensional temperature, and theta is 1 at r equals 1, decays to 0. Okay, so we are going to first consider Peclet much smaller than 1. Now, the thing is that for small Peclet, the effect on the heat transport is small. We will find that Nusselt only increases by a small amount, which is order Peclet, and for a linear flow, it's actually square root of Peclet. But the qualitative effect of the temperature field is enormous at large distance. It gives you the qualitative effect of convection, and more importantly, it's a very nice singular perturbation problem. Okay, so and heat transport is simpler than momentum transport. Okay, so it's easier to look at how singular perturbation goes in this simpler problem. Okay, and there is also an interesting tidbit that I'll come to at the end of this problem, because there are people, physicists, very famous ones, who are not convinced by the answer of the singular perturbation analysis. So that's very interesting. So this is the, so what happens is now there is a flow. Okay, so now it's a singular perturbation, and singular perturbation implies in this case that the solution that we just saw, which was the conduction solution, which decayed like 1 by r, is not a uniformly valid solution. And what I mean by that is, for any finite Peclet, you can always go to distances far away from the sphere where convection will become comparable to conduction. Okay? So that's why I've drawn this dashed contour, because beyond that or on those length scales, convection has become comparable to conduction. So there is a near field where conduction remains important, and the temperature does behave like 1 by r at leading order, but it looks very different at large distances. Okay? And how large a distance am I talking about? It's really a Peclet inverse. Okay? Now, how do you know this? It's just a dimensional argument. A Peclet inverse, though it seems to depend on A. I don't know if you people can see if I write something. If I just use what Peclet is, then it's going to be A times alpha by UA. So the A's cancel out, and I get alpha by U. Okay? So which means that its the dominance of convection is a mere statement of the fact that there exists a length scale there that doesn't involve the size of the sphere. Okay, so near the sphere, the temperature field does sense the finite size of the sphere, but beyond a certain distance, the sphere just appears like a point source of heat. Okay, and the temperature varies on that length, alpha by U. Okay, and that length for small Peclet is much, much larger than the size of the sphere. Okay, right. So if you want to put in the equations, then I'm going to now remember there are two regions. There is a near field where conduction is important, and there's a far field where convection has become comparable to conduction. Okay, so the far field, I'm going to call it the Ocene region, because Ocene was the first person to really recognize the importance of this, and he didn't do the heat transfer problem. He did the momentum transfer and got the drag correctly after an earlier mathematician, Whitehead, didn't do it. Okay, so that's not an easy problem, and he didn't do it in this formal way, but he got the right answer. Okay, right. So there is a near field where you have a conduction equation, and a far field where the convection has become comparable to conduction. And notice that it's for small Peclet, but the Peclet is not there here, and that's because I've chosen to scale distances not with A, because A is irrelevant in those regions. I'm scaling distances with that. So when you scale the distance with that, okay, it has the precise effect that the convection term becomes order 1, okay, which is what you want physically, because it's comparable to conduction. Okay. So there are two temperature fields, the inner temperature field, the outer temperature field, and then you do what Professor Hinch talked about yesterday. You match it. You take the conduction field to distances much larger than A, bring down the Ocene temperature field to distances much smaller than the screening length, and then patch up the two together. Okay. And they have to patch up because there exists a matching region where you have length scales much greater than A, yet much smaller than A Peclet inverse, where both reduce to the same form, which is the conduction equation for a point source of heat. Okay. And you can do the matching, and what you will find is that the Nusselt increases by an amount proportional to Peclet. Okay. Now, this seems sort of obvious, but it's not so obvious if you think about it. If you say that the Nusselt must increase with Peclet regardless of the direction of the flow. Okay. And now, if you say that expanding Nusselt about Peclet equals 0, and the natural tendency is to think, oh, there is no reason for a singularity at Peclet equals 0, so I want an even function of Peclet. Then you will say, okay, Nusselt should be 1 plus order Peclet squared, okay, but it's not. Okay, the singular perturbation has the effect that the correction is odd order Peclet, and this should be mod Peclet rather than Peclet squared. Okay, and this is interesting because I'm going to just read this brief passage from a paper in Biophysical Journal. So I just spotted this about a year or so ago when reading about bacteria, which is what the paper is about. So this is Howard Berg, who's worked on E. coli, and all of what I know about E. coli is due to Howard Berg's work, and Ed Purcell, who many of you would know, very, very imaginative, brilliant physicist. He won the Nobel Prize in 1952 for NMR. But what we guys, or most of you might know him by, is the really nice article that he wrote about life at low Reynolds numbers, 1976. Okay, it's a beautiful article, and he also has a very good book on electricity and magnetism. So, but nevertheless, so we'll go to this. So remember, this is the same equation that we are looking at. It's just that we have the mass transfer analog. Okay, and so right. So let's see the argument. So they denote the flux as J. J naught is the conduction estimate, and J by J naught minus 1 is the effect due to convection. So that's what they are trying to calculate. The fractional increase in the current collected by the moving sphere compared with that collected by a stationary sphere. So what they are worried about is, can bacteria increase substantially the uptake of nutrients by just swimming fast? Okay, does convection have an effect or not? And then they say that the increase in current is proportional to A nu naught by D whole squared, and that's the Peclet number. Okay, they say that was to be expected. The increase cannot depend on the direction of motion and can hardly have a singularity at Peclet equals 0. Okay, okay, and then they have a footnote. Approximate analytical treatments of these problems have been published. For example, I'm going to not talk about this, Akrivos and Taylor. The results are expressed in terms of the Nusselt number, and while agreeing for large values of Peclet, which we have not seen till now, the paper cited predicted a linear dependence of the convective transport on Peclet for small values of Peclet. Okay, we do not understand how that dependence can arise. Okay, so okay, so we're back to the OC. So I just wanted to talk briefly about this. So this is what I told you. This is the equation in the outer region. Okay, and the effect of the sphere here can be accommodated in the Ocene equation, but just saying that it's a point source of heat. Okay, so point source is a delta function sitting at the origin. So if you solve this equation, you will get an idea of how the temperature field in the outer region looks like. Okay? And Q here to leading order can be given just by the conduction estimate. Okay? Now, this is, if you notice, it's just the Green's function. Okay? Nice way of solving this equation is to look at the unsteady equivalent, that is add the time derivative and calculate the impulse response, which means that I add a delta function in time. So, I am adding a point source of heat at the initial instant, okay, taking, and that would give me the relaxation from the heat source that I added at the initial instant. But then I say that if I keep adding this continuously over an infinite interval, I am going to get a steady response. Okay? Now, if I can do this only for the diffusion operator. So, the Green's function is just the free space diffusion, the expanding Gaussian. I integrate it and I get the 1 by r response that we saw for conduction. For convection, what you need to recognize is that your diffusing source is just moving with velocity u. Okay? So, it is convecting in this direction at u, and it is depositing heat at every point along this line. And each of those sources start expanding diffusively. Okay? So, the heat sources far behind have had a longer time to expand, and therefore, the temperature field occupies a larger sphere of volume. Okay? And then it shrinks, and then you can draw an envelope around these shrinking spheres, and that is a parabola. It is a parabola because the diffusion rate of diffusion, which is the radius of that sphere, increases only like the square root of t, but the convective distance obviously increases proportional to t. Okay? So, that is a parabola, and you clearly see that all the heat is being pushed into a parabolic wake. Okay? So, this is the moving source of heat. So, I can now imagine that I am moving with it, so that that stationary, the flow is oncoming. Okay? And the flow, the heat diffuses out, but it is all convected and pushed into a wake. Okay? And that wake is parabolic in shape. So, the temperature field looks very different. Remember, it was isotropic and decayed like 1 by r in every direction at Peclet equals 0. Now, the behavior is only 1 by r very close to this line, and the temperature is in fact exponentially small in this region. Okay? Right. So, let us go to the next problem, which is we have the same sphere except we put a linear flow. So, I have just drawn a particular kind of linear flow.
Outside is convective.
Well, only very close to this rare stack, the line here is at 1 by r. So, it will decrease and then become exponentially small as you go in the transverse direction. Yeah. But exactly along that line, it is 1 by r still. Right. So, the other thing I want to point out, remember it is only the uniform flow that matters. Okay? So, it does not care about the near flow field, which means that that constant, whatever it is going to be same whether it is a particle or a drop. It does not depend on that. Okay? And and just since I talked about Berg and Purcell, there arises a contribution due to the flow field near the particle, but that is order Peclet squared. Okay? So, that has the property of the contribution being analytic. Okay? But it is not when it comes from the outer region. You can also reason it from the point of view of the fact that we are considering a source of heat in an unbounded domain. So, if it is bounded, okay, let us imagine that the volume is bounded, I keep a source of heat, and then in a thought experiment I keep decreasing Peclet. Okay? So, as long as the screening length A Peclet inverse is smaller than the domain size, okay, the Nusselt will scale like Peclet, the convective enhancement, but eventually for any finite domain, that screening length is going to move out of the domain, and then because the domain is finite, the analyticity arguments hold, and the Nusselt will start behaving like order Peclet squared. Okay? So, anyway, so we will go to the next shear flow, and here the lack of analyticity is very clear because we will see that the correction is larger and does not scale linearly with Peclet. So, in a sense, an ambient linear flow like simple shear that I have drawn here is stronger, is more effective in transporting heat. Okay? So, again the same thing, conduction here, the Oseen kind of equation here, and matching. So, I have to solve the Oseen equation. Remember, the transport doesn't come from here, it's driven by what happens in the outer region. And it turns out that here, if I look at the same argument, I can again come up with a screening length. So here, the Peclet is gamma dot a squared by alpha, okay? And I'm looking for a length scale that is independent of A. And that will only be possible if I do this. Because Peclet has an A squared, I should take a square root and then reciprocate so that the A cancels out, okay? And then I'll have an alpha by gamma dot to the half. This is the A independent length scale that governs the temperature field at large distances, okay? So that tells you that, remember, for small Peclet, Peclet inverse half is much smaller than 1 by Peclet, right? So the outer region has effectively come closer to the particle, okay? Right, so you can solve it in the same manner in if you want the temperature field. So in this case, it's a simple shear flow. So the velocity here is at 0. So you're 0. So the source of heat isn't going anywhere. It's sitting here. And then you can imagine again the same thing, that you put in impulses of heat at every instant, and they start diffusing out as spheres. But each of the spheres of influence is now distorted by the simple shear flow. Okay? It's stretched out and tilted. Okay? So they become stretched ellipses that align with the flow. And then the idea is to add up over all these ellipses, and you get the Oseen temperature field. Okay? Now the thing here is that the behavior of this, the distortion, depends on the particular kind of flow that you consider. So here what I've drawn is the distortion that's imposed by a simple shear flow. If you consider a different flow like a planar extension, the ellipses are not going to be rotated, they're just going to be stretched at an exponential rate along that direction. Okay? But you do that, you add up all this, and then you get these solutions. Okay? Right. But the important thing we already know is that's the scaling length, and it turns out that Nusselt is now 1 plus order Peclet to the half, okay, square root of Peclet, so obviously not analytic. And this is a hash because that depends on the particular linear flow that you consider. But the important thing is that it's an order 1 number regardless of what linear flow you consider, except if you go too close to solid body rotation. So for simple shear flow, it's around 0.02. For elongational flow, it's slightly larger. So the idea is that an ambient linear flow leads to a greater convective enhancement as compared to translation for the same Peclet number, just because square root of Peclet is much larger than Peclet. Okay? Right. And you could also argue, just simplistically speaking, what the convection does is it takes that ambient boundary condition, and instead of that being at infinity, you can imagine it being exactly imposed on loosely speaking on a sphere of radius a Peclet inverse here and a square root of Peclet inverse here. Okay? So the ambient temperature is imposed on a large sphere, and that sphere just became smaller for the ambient shear flow, which is why the gradient is larger, and therefore the transport is slightly more efficient for this case. Okay? Right. Okay. So now we will go to the next case, where definitely convection makes an important difference, where Peclet is much greater than 1. Okay, and then we will piece the two pictures together. So in this case, so the idea is, remember at small Peclet there was the small sphere, and you had to go very far, and then at a radius of Peclet inverse, convection became important. Now as you increase Peclet, that sphere of influence shrinks, and eventually at Peclet, very large value of Peclet, that sphere is practically coincident with your spherical particular drop. So in essence, convection becomes almost immediately important if you head off a very short distance away from the surface of the particle. Okay? That's because the convective time scale is so small that by the time heat diffuses out a short distance, you're just swept around and into a wake. Okay? So this is heat diffusing out of the particle surface, but it's rapidly convected and is all deposited in a thermal wake. Okay? And the important thing here is, unlike the momentum wake, At large Peclet, the thermal wake is actually very narrow. Okay, there is no notion of separation, okay, here, and therefore the dominant heat transfer all occurs in the attached boundary layer, okay, in the thermal boundary layer, which occupies almost the entire particle for the large Peclet limit. Okay, so I just need to do a boundary layer analysis here, okay, and you can see that the heat transport is going to be very large because now the temperature drops from T naught to T infinity over the thickness of the boundary layer. Okay, that's a very short distance. So the gradient is very large, and the Nusselt scales with the temperature gradient. The temperature gradient scales with the inverse thickness of the boundary layer. Okay, so if we know the boundary layer thickness, the inverse of that thickness will immediately give us what the heat transport and therefore the Nusselt number is. It's laminar flow. So, is that, does that?
Reynolds number large. So
Yeah, but remember I'm considering Stokes flow, so it's closer to mass transfer where Prandtl or Schmidt number will be much greater than 1. So Reynolds is not very large. Okay, so as an idealization, I've taken Reynolds to be small. I'll talk about in a slide where Reynolds becomes large, but I'll not talk about bluff bodies. So again, it will be laminar. Okay. Right.
the Prandtl number is small. What?
Prandtl is very large. Okay, momentum diffusion is infinitely more efficient than thermal diffusion. Okay, so now all we got to estimate is the boundary layer thickness. Okay, and that boundary layer thickness can be estimated by a simple balance of time scales. Okay, so we just add the scales to the picture that we discussed. We want to know what's the time scale to reach the edge of the boundary layer. Okay, and that if we denote the boundary layer as y, that's just the diffusion time scale. It diffuses out like this, y squared by d. Okay, but in the time, it's also swept tangentially by the flow, and if it's a particle, then it has to satisfy the no slip boundary condition. So close to the particle, there is a shear flow, right? So and the shear flow would look like this. Okay, remember, the flow increases from 0 to the ambient in a distance of order a, and that's because Reynolds is 0. There's no momentum boundary layer here. The only length scale is a. So the linear approximation for the shear flow is just uy by a, and the time it takes to sweep this distance, which is of order the circumference, is just a by the shear flow velocity. Okay, and so it takes longer the closer you are to the particle, because eventually it takes an infinite number of time, infinite amount of time when you're close to being close to satisfying the no slip boundary condition. But if we equate these two time scales, because it's never going to diffuse further than this because by the time it goes there, it's actually here, it's swept around. Okay, so just equating the two immediately tells you that the boundary layer thickness must be a Peclet to the minus 1/3. Okay, and then the heat transport must just be the inverse of this boundary layer thickness, and therefore the Nusselt, which is after all a dimensionless number, must be proportional to Peclet to the 1/3, or Reynolds to the 1/3 times Prandtl to the 1/3. Okay, that's for a particle. If we go for a drop, then the only difference is the flow. The diffusion is the same. The flow here doesn't have to satisfy the no slip boundary condition because it's a liquid-liquid interface. Okay, so there is a characteristic slip velocity. That slip velocity must scale with u. Okay, so now it need not slow down as it approaches the surface. So the convection time scale is a by u, and if you do the same thing, equate the convection time scale to the diffusion time scale, then it will be the boundary layer thickness is a Peclet to the minus half. Okay, and remember, Peclet is much greater than 1. So this boundary layer thickness is much smaller than that, and that makes sense because there is no slip to make the convection weak here. So convection is more efficient for a drop, so it doesn't let the heat diffuse out further, and the boundary layer for a drop is much thinner than the boundary layer for a particle at large Peclet. Okay. So since I know the boundary layer thickness, again I have the Nusselt as square root of Peclet. Okay. So now I know the small and large behavior, large Peclet behavior, and I can piece the two together. So I start from Nusselt equals 1, I exhibit a very weak increase of order Peclet, and then eventually I start growing like Peclet to the 1/3 for the particle. Okay. It's similar for a drop here. Remember, at leading order, the convective enhancement didn't even depend on the viscosity ratio, because it was all happening due to the ambient flow. And then at large Peclet, I increase as Peclet to the half. Okay. And again, I should remind you, all this is for Reynolds equals 0. Okay. When the convective transport dominates the heat or mass transfer situation, but momentum transport is entirely dominated by viscosity. Right. So like I said, oops. So the momentum boundary layer at Reynolds equals 0 really extends to infinity. Okay. Now we can consider the complementary situation where Reynolds is much greater than 1. So we have both momentum and thermal boundary layers. Okay. And then we can talk about if we can, there are any simple situations where we can write down relations similar to this. Okay. Now it seems intuitive that the scaling must depend on what's the relative thicknesses of the momentum and thermal boundary layers. And we are going to stick to the simplest situation. So we are going to consider a flat plate aligned with the free stream. So we don't have to deal with separation. Okay. And so we again consider what's the case for this flat plate rather than a sphere when Reynolds is very small, and a flat plate doesn't differ from a sphere. It doesn't qualitatively depend on the shape of the object. So the Nusselt must scale the same way here, which is for a rigid flat plate, it must scale like Peclet to the 1/3 when Reynolds is small. Okay. Now what about when Reynolds is large? So like I said, it depends on the which of the boundary layers is thicker. So let's take the one case first. Let's say that the momentum boundary layer, which is really the Blasius profile. Okay. So that blue line you can imagine as the Blasius boundary layer limit thickness. So that's the momentum boundary layer, and we'll say that let the thermal boundary layer be much thinner than the momentum boundary layer. Okay. So then what the thermal boundary layer sees is the final part of this profile as it goes down to 0. So that's approximately linear. Okay. So that's the linear shear flow that dominates the convection of heat. And now the question is really how far, what's that slope? That slope was, if you remember for the original case, we said that it was uy by a. So it rose to capital U in a length scale of order a. But now this is the case because there's no Reynolds in the scenario. In the boundary layer case, it's going to rise to U in a distance of order the boundary layer thickness. Okay. So it's going to rise much faster, and therefore the convection time scale. So this is, I have U y, this is like a, it's the distance to that station, but really I have Reynolds to the half here. So that's like uy by a Reynolds to the minus half. So let me just write that down. So when Reynolds was much smaller than 1, I had the near field velocity increasing like uy by a. So this was the distance of rise from 0 to capital U. But when Reynolds is much greater than 1, then it must rise in not this distance, but in a distance of order the boundary layer thickness. Okay. And therefore it must go as uy by a Reynolds to the minus half. Remember, that's the momentum boundary layer thickness. Okay. So if we use that instead of the original shear flow, we get our modified convection time scale for large Reynolds. Okay. Now if we equate this to this, then we get Nusselt is a modified Peclet to the 1/3. And how is the Peclet modified? I just replace the original velocity by the velocity times RE to the half, the boundary layer thickness factor, and I get my transport for large Reynolds, which is RE to the half times Prandtl to the 1/3. Okay. So that is, remember, when Prandtl is much greater than 1, so the thermal boundary layer is still much thinner than the momentum boundary layer, though unlike the earlier, yeah.
There is a typo slip. It's Reynolds to the 1/6 if you've taken 1/3 of 1/2.
No, so I've made this as a Prandtl. Yeah. So, right. So what John Hinch was saying is that this would become Reynolds to the 1/6. So it's Peclet to the 1/3 times Reynolds to the 1/6. But then I use the fact that Peclet is Reynolds times Prandtl, and I convert it into a Reynolds times Prandtl. Okay. Right. So now we look at the complementary case when Prandtl is very small. Okay. And that's it's actually a case we have already seen, because now this is the thermal boundary layer, much thicker than the momentum boundary layer, and the transport in the thermal boundary layer is not happening due to this thin section of shear flow. It's happening due to this large uniform flow. Okay. So the convection is just like a drop. That shear flow is not seen. It's like an effective slip profile, and therefore I obtain the same scaling as for a drop. Okay. So that's just Peclet to the half written in terms of Reynolds and Prandtl.
Not there. Not there.
Right. So now we have done translation. Let's go to the shearing flow.
Large, even though Prandtl is large, fluctuation will be there. I mean, real flows.
Yeah. So this is, I'm restricting myself to the laminar case. It depends on how large it is. So if it crosses the critical threshold, there will be fluctuations. But sometimes the threshold is large enough that for asymptotic purposes, it can be large without transitioning to turbulence. So, right. So now we'll take the case where there is no slip, no free stream, and I therefore have, I have an ambient shearing flow. The same case that we analyzed earlier at small Peclet. Now in those cases I didn't draw this picture, and that's because at small Peclet, if you remember, I told you that Nusselt was 1 plus some number times square root of, and that number remained order 1 diffusion of momentum, but not relative to diffusion of heat or mass. Right. So at small Peclet, the order 1 number there, which multiplied square root of Peclet, did not depend really very sensitively on the type of flow. Okay, so it was just some number that we gave 2 values for simple shear and extensional flow. At large Peclet, it does depend on the type of flow, and which is why I've just drawn a few sketches of how linear flows can look like, and they're all dependent on what the velocity gradient tensor is. Okay, so remember, a linear flow is where the velocity vector is this tensor dotted into a position vector. So the nature of the streamlines depends on how this tensor looks like. Okay. Right. So before we really do any problems, any particular thing, we can see what are the if we want to characterize how many parameters does the Nusselt number depend on, okay, then the original, so we are dealing with incompressible flows, so that tensor is traceless and of second order. So it has 8 parameters, okay. But then I can divide this gamma into a symmetric and an antisymmetric part, and as many of you would know, the symmetric part is the rate of strain tensor, and since it's symmetric, it has 3 eigendirections. Okay. So I have the freedom of choice of choosing my coordinate system along those principal axes, and so I reduce the parameters by 3. So I have 5, but you should also remember that I've already taken out the overall scale for the shear rate. That's in a Peclet number. So this should be a dimensionless thing divided by its magnitude. So I remove that magnitude scaling, and I have only 4 parameters. Well, not only 4, I have 4 parameters. And so really the analysis of a linear flow involves 4 dimensionless parameters, okay, and I can assign physical meaning to these. So one would be, let's say I consider a purely extensional flow. So such a flow would look like this. Okay, so you can immediately see that this has 3 invariant directions. Okay? 2 would be stretching, 1 would be contracting, or vice versa. So, in this case, what I can do is I can take 2 of the principal rates of strain, the rate at which the element expands or contracts along the 2 directions, and take their ratio. And if that ratio is 1, it implies that it is an axisymmetric extension of flow. So, this ratio is really a measure of the departure from axisymmetry. Okay? The rest is, remember, I am already in a principal axis aligned coordinate system, but those principal axes are based on the rate of strain tensor. There is the vorticity tensor or the vorticity vector that I have to worry about. So, the second parameter is really what is the ratio of the vorticity to one of these rates of extension. Okay? And the third parameter is we worry about the direction of the vorticity. So, how is the vorticity inclined to the principal axis coordinate system, and I need 2 angles for that, theta and phi. So, there are 4 parameters there. Okay. So, if I were to want to write out a general relation for the Nusselt number for the particle, I would say it has Peclet. Okay. Reynolds is still 0, so it is not a parameter. I have the departure from axisymmetry, the amount of vorticity, and the vorticity orientations. Okay. And if I have a drop, then I have the viscosity ratio entering as an additional parameter. Okay. Right. Now, so just to remind you, we found this scaling for the particle case, right? Peclet to the 1/3 at large Peclet for translation. Okay. Peclet to the 1/2 for translation, again at large Peclet. So, now we are going to linear flows, and here it turns out that we want to divide the linear flows into 2 groups. Okay. There are linear flows with open streamline patterns, and by open I mean that every streamline of the flow, when the particle or drop is sitting there, comes from infinity and goes to infinity. Okay. So, those are the linear flows that lead to open streamline patterns, and these tend to behave in a manner exactly similar to translation. Okay. So, I can have axisymmetric extension. So, I have just what these pictures show you is the surface streamline pattern. Okay. So, those 3 are drops. So, you can see that this is an axisymmetric extension, which means that the flow converges along this axis and then spreads out radially in that plane. Okay. So, those are the surface streamlines that are indicative of the actual flow field. So, you can see they all start from an inlet point and then go out, and there is a symmetry. This plane is a plane of symmetry. So, they will be coming out from the opposite end and also converging to this point and then going out. Okay. Yeah.
Parameter, but you have streamlines converging and diverging. So, non-dimensional parameter, why there is no pressure gradient?
Well, in Stokes flow, you do not need a pressure gradient for streamlines to converge or diverge. A linear flow does not need a pressure gradient. Right. Okay. So, this is the surface streamline. So, you can imagine that if now I had this drop being hot in a cold ambient, okay, then the thing would come, the ambient flow would be like this. The boundary layer would start at the inlet, okay, grow, and then go up to that point, and then the heat would be transported like this. Okay. So, the wake is really spans the x2, x3 plane, this plane of symmetry, and there are 2 inlets at the poles. Okay. So, that is how the boundary layer profile would be. So, then the boundary layer thickness would be the same. In other words, if this is a drop, the argument is local, right? It did not depend on the global nature of the flow. It just relies on the fact that there is a local balance between the convection time scale. Where is that? Right there. So, that is the drop. So, it does not depend on the global nature of the flow, but I have told you that what the global nature of the flow is. It is open streamlines, and we will see why that is important. But here the convection is just A by U, balance is diffusion. That same argument holds for a linear flow. So, in all these cases, the Nusselt will still scale as Peclet to the 1/3. Okay. So, this is axisymmetric extension. This is the same thing except the extension is no longer axisymmetric. So, they do not go there. They almost reach there, but then come down and join this point. Okay? And this is a picture. So these three are pictures of drops, and this is the picture of a particle that I've taken from Bachelor, who published a very nice article analyzing all of this in 1979. Okay? The particle case. And he has plotted this, what he calls the surface streamlines. Now, I'm just said this because in drop, obviously, there's a flow at the interface, and so the notion of surface streamlines makes sense. Okay? For the particle, it's a no slip condition if the particle is not rotating. So these are actually lines pointing along the local stress vector. So you should imagine that there is the simple shear flow that we spoke about, and that simple shear flow certainly has a direction, even though the magnitude shrinks to 0 as I approach the surface. Okay? That's the direction of the stress vector. So if I take that direction of the stress vector and plot it, then I get what are effectively the projected surface streamlines, okay, for a particle. But once you get those things, the scaling is the same, Peclet to the 1/3. Okay? So linear flows, when they lead to open streamline patterns, the complete picture is again similar to translation. It's different here by a small amount. Remember, the enhancement was square root of Peclet, but then at large Peclet, it does grow like Peclet to the half for a drop and Peclet to the 1/3 for a solid particle. Now, I don't think I'll do it here because it's difficult to follow, but the way you do this analysis is you look for a similarity solution. Okay? So you say that the boundary layer is a function of some angular coordinate, okay, and you will look for a similarity. So I'll just write down the functional form. So for the axisymmetric case, okay, this is very easily done. Okay, so you want a spherical coordinate system with its polar axis aligned here, so that each of these streamlines corresponds to a meridian, right? It's a line of constant phi, and things are independent of phi. So you have an equation only in r and theta. Okay, the boundary layer starts from a finite thickness at theta equals 0, and then grows as theta increases, and eventually actually diverges at theta equals pi by 2. That divergence is just the presence of the wake that I told you about. Okay? So you look for a solution that temperature field that is a function of a similarity variable eta, and eta is okay, so r is really the distance from the surface. That's what matters, right? For a boundary layer, the actual radial distance is just the radius of the drop. So it's the distance away from the surface that matters, and this is scaled relative to a boundary layer thickness that is now a function of theta. Okay? So the boundary layer grows from theta equals 0, a finite value, to infinity at theta equals pi by 2. Okay? So it's easily done here, but you can extend it here. So what Bachelor did for this flow was use something called von Mises coordinates. So people who do boundary layer theory might be familiar with this. It's a coordinate, it's an orthogonal coordinate system with one of its directions aligned along the streamlines. Okay? And you have to do this because here there exists a simple coordinate system, the spherical coordinate system, which is aligned, which has one of its coordinate lines aligned with these streamlines. But here it's more difficult, so you have to actually construct a coordinate system, one of whose coordinate lines is along the surface streamlines. Okay? You can actually do it sort of more elegantly in a different coordinate, which is the c tau coordinates, and this was put forth by John Hinch first in 1971. So I'll talk about it later. The difference between these two coordinates is this is an orthogonal coordinate system, that is a non-orthogonal coordinate system. Seems difficult, but it actually works out better here. Okay? Right. So this is the picture. So now we'll go to the second case, where linear flows actually lead to closed streamline patterns. And I'm going to so there is, you can show that this is just a, sorry, the only planar linear flows do this. And one of the planar linear flows is an important flow. So I'm going to discuss the entire family. That's simple shear. It's an important rheological flow. Okay. So the planar linear flows actually form a one parameter family. So that's how the velocity gradient tensor looks like. Parameter is alpha. Okay. So alpha takes values starting from 1 down to -1, and the flow streamlines look like this. So when alpha is 1, so alpha is like I'm sorry, I've got it wrong here. Alpha should be 1 minus alpha should be the ratio of the vorticity in the flow to the extension. Okay. So when alpha is 1, there is no vorticity. That's just stagnation point flow. Okay. As alpha decreases, you have vorticity, and that, loosely speaking, the original principal axis are orthogonal, and it rotates the principal axis together closer until at a value where the vorticity and extension exactly equal each other, those axes become coincident, and you have a unidirectional flow, the only unidirectional linear flow, which is simple shear. And then once vorticity overwhelms extension, the streamlines are closed. Okay. So these cases, it's obvious that the streamlines were closed even in the absence of the dropper particle. So they'll remain closed even when you add the dropper particle. But here it turns out that if you add a particle or a drop, the streamline is become closed, and that's crucial to the heat transfer problem. We'll see why. Okay. So these are the flows that I'm going to talk about now. The so-called hyperbolic linear flows that lie between simple shear and planar extension as the limiting members. Right. So now, why do we need to worry about closed streamline patterns? And that's because we are at Reynolds equals 0, and I'm just showing you the pattern. So we said that it occurs in these flows. So I've just taken simple shear. This is a particle in there. So once the particle goes in there, this is how the streamline pattern looks. Okay. And that's because the particle, once you immerse it in the flow, it rotates, and once it rotates, it drags the fluid around with it, and so the fluid moves in circles. Okay. So that's the 2D picture. This is the 3D one. If you go to a different hyperbolic linear flow, it's still the same. So this is, remember, these are all the open streamlines. These are all the closed streamlines, and there is a separatrix envelope which which contains the closed streamline region and separates it from the open streamline. So it's sort of like a pendulum phase plane, except that -pi and pi have been stretched out to infinity. Right. So here you again have closed streamlines, but they don't extend to infinity. So it's a finite bounded volume around that particle. Okay. Right. So one question is, okay, the particle rotates. Why does the fluid have to go around and return to its initial point? It could spiral in, spiral out. Okay. And that doesn't happen because of something known as the principle of reversibility associated with Stokes equations. And so mathematically, what happens that you can show that for the Stokes equations, if UP is a solution, then -u minus p is also a solution. Okay. So if your boundary conditions, let's say that you have solid boundaries moving with velocity capital U. Okay. And now you reverse the boundary motion. So capital U becomes minus capital U. Then it turns out that this becomes the solution instead of that. Okay. So reversing the boundary reverses the entire Stokes flow. Okay. So loosely speaking, if you reverse the boundary, you go back in time. Okay. And so this is interesting because there is obviously a microscopic reversibility that's associated with classical mechanics. Okay. So this is not microscopically reversible, of course. You're only reversing the macroscopic flow. You're not reversing molecular motion. Okay. The entropy still increases as you do this. Okay. Right. So but the thing is that the reversibility leads to a lot of constraints. So you can use reversibility arguments in this case to argue that the streamlines must be closed. Okay. So we will consider the hyperbolic linear flow that we did earlier, that one. Right. So I put a particle in there. Now this linear flow has vorticity. Remember, if it didn't have vorticity, those two invariant directions would be at right angles. That would be planar extension. So this has vorticity. That vorticity will cause that particle to rotate. Now let's imagine that I didn't know it was closed. I would say that let the fluid spiral out. Okay. Now what reversibility tells me is that if I reverse the forcing, which is reverse the direction of the ambient flow, I should spiral in, because remember, I go back in time. Okay. So if I reverse the flow, I should spiral in. But now if I sit on the other side of that slide and look at this situation, it's the same thing. The physical flow looks exactly the same, except it's been flipped. Okay. And the conclusion with this is that I seem to be spiraling out and spiraling in what is really the same situation, and that cannot be possible. So that the conclusion must be that the streamlines must exactly close on themselves. Okay. So this is an example of how the reversibility argument proceeds. So you use it, arrive at a contradiction, and then say that that cannot be the case. And in this case, what cannot be the case is a spiraling behavior. And this is why you have closed streamlines, and in fact even closed path lines due to. And you know this, maybe many of you have seen this. G.I. Taylor has a very famous video on this, where he puts a blob of red dye in a cuvette and then shears it out through 3 rotations till it almost vanishes. You don't see anything, and then it magically comes back as he retraces the cuvette. Okay. It doesn't come back exactly. The dye diffuses a little bit, so it's a little bit smeared out, but nevertheless it has a stunning effect. But I didn't want to show that, okay, because that's all these are. You should remember that this doesn't always hold true, because though there is dynamic reversibility, the kinematic equations are nonlinear. So if I write dx by dt is u of x is a highly nonlinear function of x. Okay. So this will in general be sensitive to initial conditions. Okay. So this dynamic reversibility will never come about if the equations are kinematically irreversible. Okay. In other words, these equations form a chaotic system. Okay. So if the configuration is sufficiently simple, like in this case and like in G.I. Taylor's cuvette device, then you will go back to the original configuration, but that will likely not happen if the configuration becomes complicated. In other words, you start to increase the number of degrees of freedom associated with x. And well, there's been a paper on this to just establish kinematic irreversibility, and I mean, it's not, but turns out, so my PhD advisor John Brady was one of the authors here. Okay, so the idea is just, I think they subject the suspension to an oscillatory shear, okay, and there is a limit for that strain beyond which the trajectories become irreversible. Okay. So there is a definite change in configuration beyond which you cannot retrace back the path, because you diverge away exponentially from it. Okay. So there is a limit beyond which you start to observe irreversible diffusive behavior. So I also thought I could include, I'll talk about the situation maybe a little later if I get the time. This is an example of reversibility. Okay. So this is taken from an, I'm sorry, maybe I didn't cite it. It's an Mason's article. So Mason was a very prolific experimentalist in the 50s to 70s. So he has lots of very nice experiments that really go on to verify many of the things that I said about peculiarities in Stokes flow. And so this is the case where he's dealing with a suspension of rods, non-isotropic particles, and he shears that suspension. So each of the particles rotates, and then he looks at how the orientation distribution of those rods evolves with time. Okay. Now because the rods rotate, there is a periodicity in it, and so the orientation distribution actually has a periodic component. Okay. But if the rods are not exactly the same aspect ratio, and they are not experimentally, then there is a slow damping to some steady state eventually. Okay. So this is the forward in time behavior. Okay. And then there is a case where they were worried about the reversibility of the Stokes equations. So they did a flow reversal, and you can see that starting from there, they actually get the opposite anti-damp trajectory. So, they manage to go there before it starts damping out again. Okay. So, I just thought it was interesting. So, I have called it an H and an anti-H trajectory, where physicists would know that there is a thing called the H theorem associated with the Boltzmann equation. So, you always observe trajectories along with H increases, and the idea is that it's absolutely improbable in a macroscopic system to observe a trajectory along which H would decrease. Okay. But here you can do it, okay, though it's not always the case. Right. So, now why worry about open versus closed streamlines? So, we will compare the two scenarios. So, the first one is the open streamline case. So, here we just did the scaling arguments. We found that for a solid particle, the boundary layer thickness was the inverse cube root of Peclet, and therefore, the Nusselt number had to grow with the inverse thickness of the boundary layer, which is the cube root of Peclet. For the drop, convection remained important right till the surface. There was a slip which led to a more rapid growth of the Nusselt with the Peclet number as the square root of Peclet. Okay. Now, what happens in closed streamlines is, remember, the streamlines don't come from infinity and go to infinity, they remain within a bounded domain. Okay. As a result, if you start to convect heat, then you just convect heat round a closed path, it never goes out. Okay. So, what that convection does, it rapidly makes those streamlines isothermal. Okay. So, in a very short time, each of the streamlines is of the same temperature, but then beyond that it cannot do anything. Okay. So, after that you need very slow diffusion to transport heat across the closed streamlines before you reach the open streamline region, where it is again rapidly washed off to infinity. Okay. So, what happens is that this really becomes a diffusion problem. Okay. Remember, we solved the diffusion problem in the absence of flow, where the constant temperature surfaces were spheres. Okay. Now, here the only difference is we have to solve a diffusion problem with the constant temperature surfaces being the stream surfaces. They are not spheres, but they are whatever are the surfaces associated with the Stokes velocity field. Okay. So, it becomes a more complicated diffusion problem, but what you can say is that the Nusselt number will not depend on Peclet. It was 1 for a sphere in the absence of flow. It will be again some order 1 number for this case, except that order 1 is related to the geometry of this closed streamlines. Okay. So, even when Peclet is much greater than 1, provided Reynolds is 0, and this is important, the Nusselt number will not grow with Peclet, will instead saturate at an order 1 value. Okay. So, what happens if we look at again our 1 parameter family of flows? So, there are 4 flows here. This is alpha equals 0. So, that is simple shear flow with the particle inside, and you can see that closed streamline region extending to infinity along the flow direction. And then as you add extension, more and more extension, or remove vorticity, that closed streamline region starts to shrink. But there is still one region around the particle. And finally, when you go to alpha of 1, the closed streamline region has disappeared, and streamlines, even the closest streamlines to the particle, are coming and going to infinity. Okay. So, now what happens is that is the case we have already looked at, right. It is a linear flow with open streamlines. So, in that case, the Nusselt number starts from 1 and then goes off along with a 1/3 slope on a log-log scale. Okay. But as soon as you make alpha non-zero, it does go to a certain extent, but then beyond a certain Peclet, it saturates out, because here what has happened is, so what happens is really the boundary layer starts thinning. Okay. Now, there is another length scale there, which is the thickness of the closed streamline region. Okay. So, once the boundary layer starts thinning with increasing Peclet, and at a certain point it becomes thinner than the closed streamline region, and at that point convection can no longer do anything, and the Nusselt number saturates. Okay. And this happens earlier and earlier as you go towards simple shear, because the closed streamline region is expanding. Okay. So, at a lower Peclet, the boundary layer recedes within the closed streamline region, and Nusselt tends to what I call a geometrically limited value. Okay. Right. So this is the idea again. So I'm going from a vorticity dominated linear flow to a completely extension dominated linear flow. The closed streamlined region shrinks, okay, and therefore the Nusselt number would approach a constant in each of these cases, okay, and that constant is really determined, loosely speaking, by solving the conduction problem in this domain. This is the outermost closed streamline. That's your outer boundary that's sitting at T infinity. This is the particle that's at T naught. You have a complicated domain to solve the Laplacian over, but that can be done. It will just give you a number. Eventually, you don't have that domain, and then your Nusselt number grows to infinity as Peclet increases to infinity. Right. So I spoke about a particle. Now notice that for a particle, so this is all for a particle, as soon as you add vorticity, so let's go back there a little bit. As soon as you add a vorticity, which means except for this flow, all the other flows have closed streamlines. Okay? So you're going to eventually run into a diffusion barrier for any of these flows except that. Okay? Now what if I put a drop in there? Okay? Now the interesting thing is, this is not the case. So this is again I have the same family of linear flows. Okay? So just the same sketch. Now I have an additional parameter, remember? So one parameter is the flow parameter, which tells you how close, what is the ratio of extension to vorticity. The other parameter is the viscosity ratio. Okay? So lambda is the viscosity of the drop to the viscosity of the ambient, and lambda equals 0 is the bubble, okay, and lambda equals infinity is the solid particle. Okay? So I have two parameters, alpha and lambda, and so I've just sketched the streamline pattern in the plane of symmetry around a spherical drop. Okay? And what happens as I'm going from here to here? So this is for a particular value of alpha. So it's alpha equals 0.25. Okay, remember, only for alpha equals 1 did I not have closed streamlines. In every other case, I would have closed streamlines if it were a particle. Now alpha is 0.25. But I have an open streamline regime. So here, okay, so here in this case, so I don't want you to look at these details. There are 4 stagnation points right on the surface of the drop. Okay, so there are separatrices emerging from there, and so there are 4 groups of open streamlines. One that goes from here to here, the other that goes from here to here, and there are 2 that recirculate from here to here, and then from there to there. Okay? So every streamline is open at that viscosity ratio there. Okay? And then when you come to this viscosity ratio, then they are still open, but when you finally increase the viscosity ratio beyond a certain point, the stagnation points, this stagnation point here moves outside the drop. So here it's sitting inside the drop, these 2 pairs, 1 and 2, they sit inside the drop, and then they move outside, and when they move outside, they start to enclose a closed streamlines between them and the drop. Okay? So the idea is that for any particular flow, if you increase the viscosity ratio beyond a certain threshold value, you start to have closed streamlines around the drop. Okay? So if I want to summarize this, I have Nusselt as a function of the flow type and the viscosity ratio, okay, and I can draw a critical curve here, the critical viscosity ratio curve, which is this. Okay. On one side, if I am at viscosity is greater than this critical value, I will have closed streamlines, okay, and if I am on the other side, I will have open streamlines. Okay. And this is important because now if you imagine I'm talking really of a Nusselt number surface on this plane, right. So on this side where the streamlines are open, we know that the Nusselt will grow as the square root of Peclet. Okay. On the other hand, there the Nusselt is going to remain at an order 1 value. Okay. So as Peclet goes to infinity, this side goes to infinity, that side remains at an order 1 value. Okay. Right. So, I'm not going to show you any details of this calculation, but I'm just going to show you how one might go about it. Okay. So, and that involves the coordinate system that I talked about earlier, right. So, the first thing is, so like I said, here is the open streamline region. The heat transport actually becomes more efficient with convection, but there it doesn't. It eventually hits a wall. Okay. So, one question would be that, you know, I've assumed a spherical drop, and what happens if the drop deforms? Okay. Does this flow pattern change with deformation? And it doesn't. Okay. So, this is again experiments by Mason, where he released a dye close to the drop, and it remains in a bounded region for a long time. Tells you that even with the deformed drop, there are closed streamlines. Okay, and this is just comparison of the deformed shape with the leading order spherical shape. So, the deformation will really depend here on the ratio of the viscous stresses to surface tension. Okay, so, there is a parameter called the capillary number, and the sphere corresponds to very small capillary numbers. There is also computational evidence. So, this is a paper by Pozrikides, who actually computed the streamlines within a drop at finite deformations, and he also finds that despite the drop deforming, the streamlines remain closed. Okay. In fact, he also finds that non-trivial pattern. If you remember, if you go back to the sphere case, there were 2 stagnation points. So, there is an 8 shaped separatrix here, and the computations reveal that there. So, though that's not relevant, it's interesting. So, the idea is that the drop deformation does not qualitatively alter the flow field. Okay. Right. So, this will be the last part of what I want to talk about. So, again we had started with the analysis for a particle. Okay. Now, for a particle, if in the closed streamline region, remember the reason why there are closed streamlines is because the particle rotates, and if the particle rotates, the surface streamlines must be circles. Okay. So, I have just drawn circles centered about the axis of rotation. So, that is the direction or the vorticity of the ambient flow. Okay. So, it spins about that axis. Now, you could ask, oh, what about the case of the drop? Okay. So, there are 2 cases here. So, I have shown you both the drop with closed streamlines, which remember lambda is the viscosity ratio. So, when lambda exceeds that critical value, which is dependent on the flow type, the streamlines are closed, though they are no longer circles. Okay. And if lambda is less than that value, they are actually open. Okay. Now, it turns out for a drop, the surface streamlines are not circles, but they have to be Jeffrey orbits. Okay. And this is very interesting. You can just use symmetry arguments to show that they must be Jeffrey orbits, and these are the Jeffrey orbits. Okay. So, you can see that they are elliptical in shape, but remember they are surface streamlines. So, they must remain on the sphere. So, if an ellipse has to remain on the sphere, it has to bend back. So, they are non-planar spherical ellipses. Okay. And they form a 1 parameter family. So, that is the C equals infinity, which is circular, and then it comes through these ellipses and finally shrinks to the point which is C equals 0. I will define C in a moment. Okay. Right. So, just to tell you what are the what is really the behavior of the Jeffrey orbits as with viscosity ratio. So, here again I have a solid particle where the Jeffrey orbits, if you want to speak of Jeffrey orbits for a solid particle, they are circles. Okay. Then as you decrease the viscosity ratio, they become stretched out. Okay. That stretching out increases progressively as you approach the critical value, and in this critical value they are almost meridians. Okay. So, each Jeffrey orbit almost looks like a meridian coming from that pole to this and this pole back to that. Okay. Except that if you are not exactly at lambda c, there will be a tiny region where it turns over. Okay. Exactly at lambda c, they are meridians, and then when you go to the other side, it splits up and you have regions of open streamlines. Okay. Right. So, now what are Jeffrey orbits? So, Jeffrey orbits are the Yeah, a trajectory is traced out on a unit sphere, and on a unit sphere, because I am talking about the orientation, it is the orientation vector, by the axis of revolution of, it is a redundancy here, of a particle in a linear flow. So, if you have a simple shear flow and I have a rod shaped particle, then it is going to rotate. And if I ask for where the, on the unit sphere does the rod, if I mark out the rod as a point on the unit sphere, how does the point move on the unit sphere as I shear the flow? Okay? And the answer is that the point moves along a Jeffrey orbit, and they are called Jeffrey orbits because this was first found by Jeffrey in 1922. Okay? So, it was first found by him for the specific case of spheroids, which are the simplest. You just stretch out a sphere along one axis. If you stretch it out, you get a prolate sphere, prolate spheroid, which is like a rugby shape object, and if you flatten it out, you get an oblate spheroid, and both of these rotate in Jeffrey orbit. Okay? So, you can see that this is the simple shear flow like this, and you have the Jeffrey orbits like that. Okay? So, that is again the C equals 0. So, C equals 0 is just the spheroid spinning about its axis of revolution. C equals infinity is its tumbling, okay? And all the other are intermediate non-planar orbits. Okay? And they become meridians when the prolate spheroid becomes very, very slender. Okay? So, the pattern is that as the spheroid aspect ratio increases, if the shear is like this, okay, it tends to flip when it is upright, the shear flow turns it very fast. Okay? Then when it is aligned, it turns very, very slowly. Then when it turns like this, it again flips very fast, turns very slowly, flips very fast. Okay? So, and when it becomes infinitely thin, then it just rotates rapidly and settles into the aligned mode. Okay? So, the aligned mode for an infinitely thin line, it can stay aligned. So, they are no longer periodic orbits then. So, in this case, if you ask for what is the period of rotation for an orbit and what is the shape of the orbit, they are all related to the aspect ratio of the spheroid. So, that is the governing parameter which decides the shape of the orbits. And in fact, later Francis Bretherton showed that this is not only the case for spheroids, and almost any axisymmetric particle will rotate in such an orbit in a shearing flow. Okay? The only difference is that for a spheroid, the shape parameter is the actual aspect ratio. For a general axisymmetric particle, it is some effective aspect ratio that is related to the actual aspect ratio in some way. Okay? Right. So, these are the equations. So, these are the orbit equations in spherical coordinates. R is the aspect ratio of the spheroid. Okay? Those are the Jeffrey orbits. You can see theta is the polar angle with respect to the z axis, that is the ambient vorticity, and phi is the azimuthal angle. Okay. Now, you can actually solve this, that is fairly trivial. Okay. So, and then when you solve it, you can get two constants of integration. So, one constant of integration, which is c, and then there is a tau. Okay. So, you can think of tau as the phase of the orbit and c as an orbit constant. So, that is the orbit constant, which is what I was using earlier to describe or label each of these orbits. Okay. So, c is obviously the orbit constant because it is the label of a particular orbit, and tau measures the how time progresses along a given orbit. Okay. Now, like I said, for an actual axisymmetric particle, the parameter gamma is actually related to the geometrical aspect ratio. It is related to the geometry, but for a drop, remember we saw these surface streamlines, closed surface streamlines. It is not, it cannot be related to the geometrical aspect ratio because remember the drop is a sphere. Okay. It is actually a function of both the flow, where beta is a function of the flow, and the viscosity ratio. Okay. So, this is the effective aspect ratio that tells you the shape of these streamlines. Okay. So, now I am going to be very brief here. So, the idea is that let us just go back for a minute to the solid particle case, large Peclet. Right. So I told you that the solid particle case, the analysis would proceed by having a streamline aligned coordinate system, okay, and you track the growth of the boundary layer along the streamlines. Okay. You would do exactly the same for a drop, except not in von Mises coordinates. That turns out to be complicated. You can do it in C tau coordinates. Okay. So each of the C marks out a streamline or a Jeffrey orbit, and tau is the time measured along that streamline. Okay. So tau is the analog of theta, okay, and C is the analog of the streamline label, phi in this case. So you can do this. The thing that I told you, like I said, John Hinch in a paper with Gary Leal first used this coordinate system in a very nice way, and I would really encourage people to look up that paper, JFM 1971. Okay, the nice thing is, and which makes it not trivial, is that the coordinate system is non-orthogonal. Okay, so if you know how to use it, it's very nice. Okay, and so you can do this, and you have non-trivial metric factors and so on, and you can calculate. So you write down the convection diffusion equation in C tau coordinates, and do the Nusselt number integral in C tau coordinates, and once you do that, you get the Nusselt number surface for a drop. Okay. So remember again, so I have not plotted the actual Nusselt number. The Nusselt number in this case will scale with Peclet to the half, that we know. So this is really the prefactor. So what we can say from arguments is that the Nusselt number will be a function of the two parameters alpha and lambda times Peclet to the half. So this is that function of alpha and lambda. Okay. And such a scaling exists only on the open streamline side, remember. So that's the critical viscosity curve there. Okay. And when you're for values of viscosity below that critical viscosity, you are in the open streamline regime, and you can calculate the Nusselt number. So that is the result of the boundary layer analysis. And I don't know if I mentioned this. So this is work done by Deepak Krishnamurthy, who is just graduating with an MS from JNC. So he's worked with me for the last 3 years. Okay. So right. So then there exists the lambda greater than lambda c, where I'm just going to mention that when there are closed streamlines, then the deviation from the Stokes paradigm becomes important, and you got to consider effects of finite Reynolds number. Okay, because what happens is when Reynolds number is finite, then there are centrifugal forces, inertial forces, which break open the closed streamlines, and once the closed streamlines break open, you can again have convection carry the heat away. Okay. And so you can calculate a Nusselt number driven by the inertial flow. Okay. So I'm just going to show you this final picture. So this is again the Nusselt number prefactor as a function of alpha and lambda. That is the open streamline side. So that is the surface that you already saw, and this is the closed streamline side. So here Nusselt scales as Peclet to the half. Here actually it scales as Reynolds times Peclet to the half, because inertia is crucial in this thing. Okay. And there exists some sort of a kink because something else happens in between. But this is the Nusselt number surface as a function of alpha and lambda, and you can see that it looks very different on the two sides of that critical viscosity curve. Okay. So yeah, so that's a good point to end. I'd be happy to answer any questions that you have.
So your analysis is basically based on boundary layers, no? The Nusselt versus Peclet. But in the bulk itself, there will be some balance of the terms. So I did this for Rayleigh Bernard, that's why I'm saying. So in the bulk, if you match the terms, do you get similar scaling? I mean, it should get the same scaling. So bulk, okay, you get my point.
Yes, I get your point. So, but I mean, you get the 1/3 scaling by usually saying that it's boundary layer driven, so it should be independent of the bulk dimension. So that's how I thought you come up with that. You're talking about the Rayleigh proportional, the heat transport in Rayleigh Bernard proportional to the 1/3 power of the.
Yeah, so actually that 1/3 is quite mischievous in Rayleigh Bernard. It's very contradictory, rather controversial.
Yeah.
But Peclet going as square root Rayleigh can be gotten quite easily by the bulk flow, which I can show you that argument.
Okay.
So I was just wondering whether if you just, so this is all fine, I mean, but if you just mass the terms in the bulk away from that, what is it, I mean the separatrix, then you should get similar scaling for consistency at least.
But so the thing is that there are no temperature fluctuations in the bulk. Everything happens in that bounded layer. If you go outside, T is T infinity. So
I see.
So it's nothing's happening there. Everything is happening in this tiny region.
I see. Okay, it's different then. Okay.
Yeah.
So it's a very nice worrying study of what's happening outside the particle. When it's a drop in particular, one might have to worry about what the heat transfer is inside. And it may not be at the set temperature T0.
Yes, yes. And that seems complicated because you saw the streamline pattern within the drop. Yeah. So